Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the first part of the fourth video lecture and it's on the application of the finite difference method. And after a very brief introduction, you will be introduced again, probably, to Taylor expansion and how to construct finite differences from that. The sources of literature in this topic are many. And I've chosen only to list the course compendium section 5.6, which is exactly on the discretization of the Reynolds equation by means of the finite difference method. But for the interested reader, I've also chosen to list the book Multi-Level Methods in Lubrication, which also involves quite a lot of detail and important such on the discretization. The outline of the presentation looks like this. So it starts with a very brief introduction and then it's a recap on the Taylor expansion and how to compose finite difference schemes from it. And then in the second part we're going to first discretize the Reynolds equation in 1D, and there will be an example of a very simple form of the Poisson equation. And then we're looking into the discretization in 2D. Finally, in part 3, we will again look at the concept of force balance, and it will be very similar to what we've seen before, but now we discretize it, and then we talk about some numerical issues. Let's start by having an overview of some different solution methods. So here we have the advantages and the disadvantages of the analytical solution, or semi-analytical solution if you like. Of course, an advantage is that it's exact, so it's correct. It's not up to some numerical discretization error or some numerical specified tolerance or so. It's also very fast, it's just a computation. And we can study trends, like, effect of different parameters is easy. It's just to see exactly what the response is in the analytical solution. Disadvantages. So of course we can only consider very simple cases. The most simplistic cases can be studied by means of an analytical solution, as it's only possible there to obtain it, to solve it analytically, the problem. And it's little flexibility for further improvements because we cannot add new feature to it. It's not solvable then. There are various different numerical methods. One of them is the finite difference method, which we devote quite a lot of attention to in this video. And here we can handle more complex cases, of course. We have quite good control as a user of exactly what the solution procedure does. It's easy to program, but it's not so good for complex geometries. And I don't know, but there are nearly no commercial software available for this type of method, but a lot of in-house routines built on finite difference to benchmark and test the validity of finite element solutions. So the third one is the finite element solution, and the good thing with this is that it can consider almost any geometry. The meshing can of course be a little bit of a problem. There's a lot of commercial softwares available. It's more complicated to program, and in case we're talking about the commercial software, it's definitely less control by the user. Let us start by dividing the domain from xa to xb into n+1 equally large intervals. So the interval length can be defined as delta x equal xb minus xa over n+1. Now consider also the function y equal f of x. By means of our discretization, we can consider the values of these functions at different points, and we define by fi the value of f evaluated at the point xi. Now, Taylor expansion can give us expressions for the values of fi plus 1 and fi minus 1, as they are just the function f evaluated at xi plus minus delta xi. And these are the Taylor expansions for those 2 points. And we note that the last term, ordo x delta x cubed, is a residual which is of the order delta x cubed, and delta x cubed is much less than 1 for a small delta x. So without too much of an error, we may perhaps neglect this term to obtain a finite difference scheme. Let's see. So we start by looking at forward derivative approximation. And this is the one that we may obtain from considering the Taylor expansion for fi plus 1 over here. So let's now subtract fi from both sides and then divide by delta x. Then we have this fraction fi plus 1 minus fi over delta x, which is now equal this new right hand side, and we now can solve for f prime of xi, and if we do, we obtain exactly this expression below, and we can clearly see that if we only consider this ratio term, then there must be an order of delta x term left, i.e. the one with the coefficient that is the second derivative of the point of f in the point xi. Similarly, we can obtain a backward derivative approximation, also called upwind derivative approximation, by considering the Taylor expansion for the function in the point xi minus 1. Doing the same and solving for f prime in the point xi gives this ratio fi minus 1 over delta x plus an order residual term of the order delta x. So this also has a first order error of the approximation of f of x if we just neglect those terms. A central derivative approximation can be obtained by subtracting the Taylor approximation for the function in the point xi plus 1 with the function in the point xi minus 1. And what we see here, below the subtraction sign line, we get the difference between fi plus 1 and fi minus 1. And on the right hand side of that, we have an expression involving the derivative of the function. So we can solve this now for the derivative of the function in point xi, which we have here to the right. But now look at the term, the order term, which defines the residual. And we clearly see that now this residual is of the order delta x squared. So this is a second order approximation of the derivative. And this is more accurate in general. However, it's not always that we can use this type of central derivative approximation. We may need to have a second order upwind or forward discretization instead. But it's more accurate in general. So remember this. Another way of obtaining a central derivative approximation is to consider the function in the points in the middle between two nodes xi. So we consider it at the nodes xi plus minus 0.5 at the half mesh size. And precisely as before, we do this by taking the Taylor approximations of a function in those points now, we subtract them from each other, and we solve for the derivative of the function in the point xi. And we can now see that this is also a second order approximation, which is more accurate in general than a first order. In order to obtain a central difference for the second derivative of a function, we can add the two Taylor expansions below together, because then the terms involving the derivative, third derivative, and so the odd derivatives, they cancel. And left is an expression which we can solve for the derivative of the second derivative of f in the point xi. When we do and express that in index notation, we have the following result, which is also second order accurate in terms of delta x.